welcome to episode number 24. Okay, just a gentle reminder, the quiz 23 to 25 we'll be doing tomorrow. And there's no PA doing this week. Great. The topic for the morning, the first hour is going to be IPv6. And before that, we need to finish quiz 27. But shortly after we finish IPv6, we'll actually run into yet another quiz, quiz 28. But 27 and 28 are more open, okay? Just a way to get you into thinking some of the key questions. And then the second half of the first hour is going to be SDN. Okay, so this is the first serious discussion about the software-defined networking. But in the lecture today, the part of SDN we'll be examining is just the forwarding side. Okay, we'll talk about the routing side in chapter 5, which is coming, I think, 2 weeks from now. So let's go ahead and go back to quiz 27. Yeah, it's called the ideal versus practical. Okay, so what is the better solution in terms of being more practical versus more ideal? So part 1 of quiz 27 is asking this. Would you rather pay for having multiple IPs for the multiple machines you have at home or using just NAT? Okay, so pick one and then give me a reason why you pick one of these two. And then part 2 is asking, would you prefer to use NAT or IPv6? Okay, if you recall in the lecture yesterday. So there's actually some debate, right, between whether we should use IPv6, which is to extend the IP address space to 128 bits so that we get away from this IP address shortage problem. Instead of using NAT, the device is controversial because it's actually changing the packet header, both in the layer 3 as well as layer 4. Okay, so which one would you prefer and why? Let's make it 3 minutes. So feel free just to tell the intuition. Okay, I see team 1 here saying, yeah, paying for multiple IP addresses. Okay, because the reason is that it feels better having control. Okay, willing to pay more. Yeah, probably because you would like to set up servers from time to time so that it's easy to connect to the home machines from outside. And, okay, so Team 1 prefers IPv6. Yeah, being able to address things directly to a machine, it gives actually advantage as well, yes. Yeah, domain names are very cheap these days, yes. Okay. Yeah, IP address is something that's a lot more scarce because the format is more limited than the names. So definitely pushing for IPv6 from Team 1's point of view. Okay, good. I guess that for many of you, yeah, the problem is a bit more open. So feel free, just tell the intuition. As we move on to the first topic today, it's IPv6. So some of you might still be, debating, what exactly is IPv6? I'm not quite sure whether I want to choose NAT or IPv6. Now, here's
Last
more.
topic in 4.3, the IPv6. This is also the protocol some of these network engineers thought more legit, addressing the IP address shortage problem, instead of using these controversial net boxes. And that is why we actually upgrade from version 4 to version 6. The approach is very straightforward, expanding the 32-bit IP address space to 128 bits long. So the main goal of having IPv6 is exactly this. There are two secondary goals. First is to speed up the processing or forwarding of the packets as they come into a router. So in the data plane, packets coming in really fast. If we could reduce the forwarding time, processing time, we made the transmission process as efficient as possible. So you'll see in IPv6, the header is also changed to try to reduce the forwarding time, the processing time. The secondary purpose, this. We want to add something so that we could label the packets, so we could separate a group of packets from other, and make them flows, different flows. Now, with the different flows of these packets, we could then assign priority to a specific flow versus lower priority for other flows. Therefore, we could establish a more flexible levels of quality of service for these different flows. You see also header fields there to support labeling of flows, setting priority of the flows. The IPv6 packet format. The header part of it is fixed size and 40 bytes long. Now recall version 4. Is it fixed size or variable size? It's actually variable size because of the option fields there. So that field, in case we have more options, then it's going to go longer. No fields, 0. And therefore, IPv4 header size is 20 bytes minimum and could potentially be more. Now you probably recall, right? When we were talking about the IP header size, 20 bytes, we also mentioned the TCP header, 20 more bytes. Together, 40 bytes, just to store the control information. If we're sending a real message that's 10 bytes long, the entire packet will be this long, while only 10 of them is effectively sending data. This is very low utilization. So yeah, Poly kind of promised you that in the next version of IP, we're going to reduce the size of the header. But you see here, is 40 longer or 20? 46, in fact, has a longer header. But this is necessary, and this is as small, as short as possible already. Allow me to explain. In the IP packet header, there are two fields called the source IP and the destination IP. In version 4, the IP address space is only 4 bytes long. Now, to store source and destination IP, you only need 8 bytes. But in version 6, the main goal is to expand the IP address space So unavoidably, we have very long IP address and two of them, one for source IPs, another one for the destination IP, together 32 bytes. If you look at this, version 6 header 40 bytes, so we have only 8 bytes for the additional fields. While in version 4, 20 bytes long, we have 12 bytes for the additional fields. So the designer of IPv6, you see, try very hard to reduce these other unnecessary part of the header, removing them away, removing these fields away from the header. Okay. So 40 here, longer indeed, but it is actually after we try very hard making the header part as compact as possible, as small as possible. In fact, the second feature of the version 4 header is this. To recall in the fragmentation and reassembly function of IPv6, we have these 3 fields in a row. ID, fragmentation flag, and offset. This row of extra header fields remove entirely, okay? And this is done by disabling the fragmentation and reassembly function in version 4. So in IPv6, no longer allowing fragmentation. And this is why we see the version 4 header, although longer, it looks really clean and compact. Okay. First, the source address, second, destination address. And the rest is only just 6 more, 1, 2, 3, 4, 5, 6. First, here is the payload length. If you recall in version 4, we do have what? The header length and the entire packet length. Because the header size can vary. And the packet size, because the data size can also be different, so we need 2 lengths. Here now, having a fixed packet header size, we need just the payload part, okay, the payload length to indicate the size of the data down here. Hop limit, this is just a TTL field, okay, just like in IPv4. Next header, it looks odd, we've never seen this before, but this is really the upper layer field in version 4. So what it does is, once we extract the payload, we actually forward the payload to what's indicated by this pointer here. And so further processing will be done using this handler on the payload. The version field, we also have this in version 4. So the only difference is that this value will always be 6 in version 6. Priority and flow label, these two are new. So flow label here is to allowing us to group a specific set of packets together. Okay, so coming from one application, coming from one service, they could be carrying flow ID 1, and other packets from other services, flow ID 2. So we could identify packets for one flow, okay, and packets for yet another flow. So we could separate these packets traveling the internet. As a result, we could then provide different priorities to different flows. So some flows will go earlier than the others. Therefore, we provide flexible levels of these QoS. Now, there are some more fields we remove, okay, not just the fragmentation fields. Header checksum in IPv4 header, that is removed because to calculate time, to check the checksum takes also time. So let's try to reduce the forwarding processing time as much as we can. So let's remove the checksum part. And take the risk of some bits in the header being flipped. We might have some, we might run into some errors, but chance is very low. Okay. We way higher here, way more here, trying to make sure the forwarding part is fast. And we move the option part down to the payload, so that when we grab the payload and give it to the handler. The handler is going to look at the first few lines in the payload, and those will contain the options. Okay. Yeah, there's one more thing. Yeah, ICMP version 6. What is ICMP? You need to think back. In one of the earlier overview slides, I was talking about the functions and protocols implemented in the network layer, right? In the data plane, we have forwarding. In the control plane, we have routing and management. ICMP is one of these protocols implementing the management function. Okay. So we also extend the version 4 ICMP to version 6. Okay. And the reason we need the version 6 ICMP is so that we could send a special message, packet too big. Okay. Allow me to elaborate. Now we don't have fragmentation and reassembly. But the fact that some of the links on the internet allows smaller MTU is still there. So what if we have big datagram coming to a router and the next link is saying MTU smaller? But we cannot fragment this datagram anymore. What should the router do? What can the router do? So the mechanism in version 6 is to send a special message, an ICMP version 6 message, back to the data source saying packet too big and the better packet size is below this MTU value. Okay, so there's additional message being defined in ICMP version 6, allowing the routers to manage themselves, deciding what is the best datagram size. And we'll just ignore this part. Multicast, we'll just not talk about it at all. Okay, it's a can of worms. So this is IPv6 packet format. So this topic is a little bit special. Okay, we will be talking about how we move from a IPv4 internet to a IPv6 internet. You see, there's no way we turn down all the routers in the world and upgrade to version 6 simultaneously and turn them back on and hope that they will just work. No way. Okay. It's really, really risky. And hey, we are all, right, living in different time zones. What do you mean by having a flat day? And not to mention that turning the entire net down for an entire day, okay, and wait until all the debugging and upgrading is done. Well, yeah, some part of the world might panic. So how will the network operate with part of the internet running IPv4 and some other parts running IPv6? So transition from IPv4 to IPv6, this is what we meant to talk about. How do we allow the mix of IPv4 router to IPv6 router? And the technique, okay, let me tell you ahead of time, is called tunneling. Okay, establishing tunnels, okay, between routers, okay, at the edge of the IPv6 network to IPv4 and then back to IPv6. And the technique is working this way. So if there's a packet generated from, the IPv6 space, so then the network layer in the machine in the IPv6 space will be generating an IPv6 packet. Okay. Once it hits, okay, this border between IPv6 and IPv4, this router standing at the border will be implementing both IPv4 and 6. Okay. So this router will also be doing this. Take the IPv4 packet generated from the take the IPv6 packet generated in the IPv6 space and encapsulate that into an IPv4 packet. Okay, so this is the IPv4 packet, okay, and this is the original IPv6 packet, okay, generated from the IPv6 space. So that IPv4 packet is encapsulated, so being contained, okay, in this bigger IPv4 packet. So you see here, we'll have packet header fields here, source IP address, destination IP address, and etc. etc. Now IPv4 packet here coming from the border of IPv4 and IPv6 connection is going to travel the IPv4 network fine because the header fields interpretable by the routers in the IPv4 space and eventually reaching the other end, okay, the other border between IPv6 and IPv4. And that border router there would extract, okay, the IPv6 packet, the blue part here, from the IPv4 packet, and then forward it further on onto the native IPv6 space here. Right? This enables an IPv6 machine talking to an IPv6 machine with the middle part being IPv4. I know, allow me to illustrate. So in the scenario, we have an IPv6 space to the left and another IPv6 space to the right. I suppose we have data we want to send from A to F. Okay? Both of them, version 6, they should be able to send data to each other all right. Now the problem is this. Yeah, an IPv6 packet here will travel through the version 6 space. But as soon as it hits the version 4 space, yeah, these routers, they're old. They don't recognize the version 4 format. They will not be able to handle the packet and forward it down this way. Okay? And that is why we need tunnel. Okay? So what's being done, okay, in the tunnel is this. B being the border router, E being the border router separating the version 4 and version 6 space. It's implementing version 6 for sure, but also version 4 as well. Therefore, B and E both carry IPv6 address as well as IPv4 address. By setting up tunnel, B now actually record E's version 4 IP address. E here records B's version 4 IP address. So essentially the two ends, okay, exchange the IPv4 address. So once that's done, usually this is done offline by the network admins. Once that is done, then let's consider, okay, A here generated the packet, the blue one, and we're forwarding it towards the destination. Right? Once it hits the border router here before the IPv4 space, B, the border router, is going to do this. Encapsulate the blue packet inside a version 4 packet. In the version 4 packet, the source address is going to be B itself. Destination address is going to be the other end of the tunnel. Okay, the other end of the tunnel's IPv4 address. Now, this is an IPv4 packet, source being B, destination being E.
Hello? Good. Yeah, network outage. Sorry, guys. Yeah, I don't know why, but it could be because that, yeah, other students or other professors are still trying to use IP addresses they can harvest. Yeah, I should really seriously registering the MAC address of the machines I'm using. But I don't like doing that because I actually use different machines to do the same thing. So for example, I'm now using my MacBook as I'm actually degrading my desktop's Mac system down to Mojave. So yeah, that could be the reason that, because it's obviously a network shortage, I did not see anything at all, no packets for like 5 to 7 minutes. Okay, but that was IPv6. You heard a little bit that it takes time to transition from IPv4 to IPv6. Okay, so the part that you didn't hear is this. Yeah, it took us already 20 years to make the transition, and we are still here. Okay, if you now think, is the IP address for the workstation an IPv4 address or IPv6 address? Yeah, I know it's quite obvious, right? It's still the IPv4 address, right? Being an institute, okay, higher education institute, where professors are teaching, it's actually better to move to V6, and yet we're still using V4. Okay, why is it so hard to make the change entirely? Right, there has been 20 years already. Okay, so it seems that making change in the network layer very hard, while higher up in the network layer. Okay, so let me move to the Q&A. While higher up in the network, in the application layer, we have new applications showing almost every year. Okay, so for example, this couple years, the hottest was Zoom, the video conferencing app, and I'm pretty sure that there will be more apps showing. Okay, but internet, the network layer, the layer 3. Okay, it's so hard to get it to change. Okay, so that is what quiz 28 is also asking. Oops, encoding overloaded. So I'll try to tune the streaming rate to something that's even lower and see if it works better. But quiz 28, let me go back to so this is actually easier for you to read given that the resolution is lower. So first part is asking this. Have you ever thought about changing your way of life? Okay, so this is a very general open question. Okay, so this is just so that you can relate to how hard it is to change from IPv4 to IPv6. Okay, so have you thought about making a change, okay, in the way you live? Q2, if yes, did you end up making the change? Okay, so you thought about it. Did you manage to make the change? Q3, if yes, was it easy? Okay, if not, then why not? What is so hard about, making the change? Think about this. This is rather open. I know for this type of question, it seems to take you more time. Okay, so yeah, think about it. Let's give it some 5 minutes. How about that? Yeah, so maybe to help you think, let me give you an example. There's one change I would like to make recently, but it requires the help from my neighbors. Okay? I don't know where you live. Many of you probably live in the university dorm. Okay, I live in this apartment building. It's not entirely new, some 10, 15 years old. Okay, so on the same floor, I do have some 4 other neighbors living nearby. Okay, so door next to doors. The thing is that, from parents and down, we seem to leave our shoes outside the door, okay? And they would just kind of scatter around in the hallway on the floor, okay? And I mean, having living in the States, in Europe for some while, I've never seen this, phenomena before. And recently, the association was promoting that we remove all the shoes from the hall and keep all the shoes inside, okay, the house. So I thought that's great. Okay, that is wonderful. Finally, okay, the hallway will look clean. And in case we need to run because of fire and things like that, there will be less obstacles. I know some of my neighbors actually leave the bikes and stuff outside, right? So, but for already 2 months, the situation has not been changed at all. Even though that I keep all the shoes of the household inside the house already. Okay, so yeah, I do want to make some change. Okay, and I change for myself, but my neighbors are not changing it. Okay, so the kind of change I was looking for is still not being, still not taking effect. So very unfortunate. And I guess it's challenging because, my neighbors are not so much about making the change. Okay, could be that they're busy. Could be that they are already used, okay, to using the old systems. Leaving the shoes outside. So that's just one one thing that I had in mind that I can share with you guys. So what about you? So maybe the IPv4 guys, yeah, already so used to using IPv4, and we have NAT anyway, right? So yeah, and then people like Rocket will have to come up with other ways to try to get access to the home machines behind NAT. So I do something like that to try to hack around. Mm-hmm. So have you run into situations like this? So IPv4 not moving to IPv6 entirely yet. Probably because, yeah, there's not enough time to make the change. And probably there's not urgent need. Mm-hmm. And those who do need it can find other solutions to get around the problem. Hmm. Oh, okay, Rocket again. Yes, yes, but there are also changes that I've thought about but haven't done. Okay. Easy to decide, harder to do. Ah, okay. Oh, okay, okay. So this is interesting. Okay. This is a good point. So, yeah, sometimes there are these changes that you really like. Okay. And it's actually easy to say that I'm going to make the change, but sometimes it's hard to really do it, to execute it. So that might be a bit more psychological, right? Part of it probably is taking time, and there's always shortage of time. And team four. Oh, this is very honest. Okay, Kevin, I want to live a more healthy life. I know, we all do. I plan to get up before 8:30 every morning. Then I can enjoy breakfast, read novels, or even do some exercise before going to school. Oh, wow. Yeah, I do the same. Did you manage to make the change? Yeah, I guess it's complicated. Kevin's taking time to type things out. All right, so let's see. Oh, David. Okay, let me go to the Q&A so you can see the type ups. David here. Yes, many times. Wake up early, for example. Yeah, I know. It was hard for me when I was younger. Q2. Some did. Okay, great. Sounds great. But some didn't. Okay, good. Okay. Not easy. Maybe due to old habits. I know. I think this habit thing, yeah, it's actually something that's slowing us down, right? Isn't it? Okay. And I don't know what this habit is doing. Because we just repeat things we do. That seems easy. The cognitive load is lower. So I guess that not using the brain is also, a good thing, an easier thing to do. Yeah, because in order to make sure that you actually do the change, right? You have to keep in mind that you need to do the change, okay? And you sometimes need to convince yourself, something like that. Everyone else has the same lifestyle. Yeah, yeah, yeah. So it doesn't matter all that much if you don't manage to make the change. Yes. Yeah. So one trouble I had is also that hey, I collect all the shoes I have outside and then move them inside, and then neighbors started looking at me like you're weird. All right, okay. I thought that is what the association decided to do. You haven't made the change yet. Lots of work. Made me go to bed late. I know. Sorry about having lots of these PAs and quizzes. So I often get up just 30 minutes before the class, okay? That might be good enough already. All right, so many thanks for the input. that actually tells a little bit more why IPv6 has been here for 20 years, but the internet is not yet entirely IPv6. In fact, only a small portion of it being IPv6. Okay, so we remain the minority. All right, yeah. So you also see a little bit. Things don't get all the time to an ideal state. All right, Jiazi. So let's go over Jiazi's solution. Me too much work for required subjects. Oh, you guys. Okay, poor you. So let's see how Jiazi is saying. Okay, maybe we should do this more. This sounds more like a support group. We complain about the things that we want to do, but couldn't, ended up making it. Yeah. So team 5 is saying, let's see, live like water meeting. Cool. Did you read the novel or did you watch the movie? Yeah. Q2? No. Oh, okay. Sometimes it's hard to get out of the comfort zone and to abandon what you already have. I know. Very hard, isn't it? Mhm. I know. Yeah. Because I got pressured into doing things that I don't really want to do more. Okay. Because somehow we all feel the pressure needing to be, friendly to others. Yeah. Me too. Too much work for required subject. Team 13. Okay. Silvercraft. Ijo is saying yes. If it's easier, change. If sometimes, consider doing it. Yeah. Oh, okay. If it's easy change, then you would consider doing it. Most changes are hard to get used to. I know. Mhm. It's not easy, of course. I may need to manage my time more effectively. Kevin, it's easier said than do it, right? Movie, yeah, it's a great one. I know. Yeah. Have you ever had large philosophical or existential changes in your life? If so, are you comfortable sharing on stream? Well, let me see. I decided that I would be honest to all my neighbors. And it didn't work out well. I'm still struggling. Okay. So what I did is that, so the example I gave you, okay. I mean, when I was growing up, my parents just, kept telling me that, hey, just, go along with the society. All right. I know they might not be, doing things that it's actually abiding to the law, but no, don't be a snitcher. Or was that? Yeah. Don't be a snitch. Okay. Don't report on them. Okay. But recently, I began to take photos of my neighbors parking illegally, okay, on these red zones, okay, and reporting to the police. Okay. And they learned about this. And I am now receiving a lot of social pressure. Okay, so the family is telling me constantly that I should stop doing it, and I'm still struggling. I might change it back. I don't know. I think this is a very big change and a very risky change. I don't know. I should continue to do the right thing or not. Okay. It's a constant struggle. I know that I should be doing the right thing, and yet I couldn't do the right thing because the right thing is right for someone but not right for some others. You see, you see, what is right? Yeah, that is always the biggest question. Okay. All right, so yeah, I openly share my struggle trying to do the right thing. Mhm. I know you share openly as well, you trying to do the right thing and make changes. Hope that you're successful on your side and hope that I get successful, okay, on my side. I guess I need to find other ways to communicate with my neighbors. So I'm thinking about it. Good. So that was actually just part one of the first hour. Okay. The second part is actually pretty long. So let me see. What I would do is that I actually will use the rest of time to play it. And that's probably just 5 minutes. Okay. Oh, you know what? This is what I'm gonna do. Let's take a break now, okay, and resume in 10 minutes, okay? And I'm gonna start playing SDN, how the forwarding side is done for 10 minutes. And then we really need to go to PA9, all right? Now, of course, I know some of you guys prefer to do PA9 while you play the video, so you could pause and then, try things out and come back to the video. That is fine, okay? But I do know that some of you actually stay through the PAs because then you get through everything at once. Okay, it would be also a slightly more efficient use of time as well if you noticed. Okay, so let's make some minor change here because sometimes the networking stuff is not that mathematical, not that a lot of these designs are more philosophical. But design is always philosophical. What is good, what is right, it really depends on how people think, right? And people always have this psychological aspect. Okay? Even though a machine is working very well, but I don't like the shape of it, I don't like the cover of it, okay? And that compromises, okay, the performance or the desire of a person wanting to own a machine, okay? So there's always a user aspect of a system. Okay, that is actually what I'm trying to communicate here. Why IPv6 is still not there for us, all of us. Okay, so let's take a break for 10 minutes and then resume and then come to the SDN part, okay, of the video. All right, so let me go to the open site and take a break. And yeah, let's come back to the lecture. So this is SDN, the forwarding side of it. So we only have time for the first part of SDN.
Last section in chapter 4, generalized forwarding and SDN. So in these SDN routers, okay, the way we're doing forwarding is actually different from the traditional one, therefore we call it the generalized forwarding. In traditional routing, if you still recall, in the data plane, when packet arrives, we look at the destination IP address and we try to match destination IP address to the prefix entries in the forwarding table. If we match one, what we essentially do is to forward the packet to the link interface indicated in the entry. So in the traditional forwarding, what we're doing in terms of matching, very specific, the destination address. What we're doing as an action is simply to forward the packet further. But in SDN routers, in the data plane, the matching and actions are now a lot more general. This is the architecture of the modern routing, or SDN-based routing. Now the separation of data plane and control plane, this part is actually very similar to the traditional routing. Now, if you recall the overview of chapters 4, you should recognize in SDN, the control plane look very different. Instead of having routing algorithms running on each individual routers, we now run the routing algorithm centrally on one or maybe a couple powerful machines. And these machines could be slightly far away from the routers in the network. Now, what's a bit similar though between SDN routing and the traditional routing is this. After route computation, we generate tables like this. Okay, this is similar to traditional routing, right? In the control plane of the traditional routing algorithm finish computation generates forwarding table, and we install forwarding table to the data plane of the traditional router. Now, in SDN, tables are generated as well from the routing algorithm computation, and we also install these tables to the data plane of the SDN routers. You see, the control plane to data plane connection there between SDN and traditional routing, very similar. The only slight difference is this. In traditional routing, we call these the forwarding tables, but in SDN, we call them the flow tables. Okay, so each router there will be installed with these flow tables to handle packets coming in. And so a flow table, if we zoom in, it looks more like this in SDN. In traditional forwarding, we have what? Prefix, the first column, and the link interface, the second column. The actions being taken is very simple, matching prefix, and then forward to a link interface. So what we're doing is always forwarding in the traditional routing. But in SDN, these actions could be more general, okay? Not just forwarding. So calling it a forwarding table is a bit awkward. So instead, in SDN, we call it the flow table instead. And by flow, SDN is actually referring to each of these entries, each of these rows in the table. That is also saying if packets coming into this router, where multiple of them matching a particular header combination and therefore take the same action, they belong to the same flow. So each row here is a flow. So we have a table of many flows in a sense. So what I'm showing here is also an example. Packets could come in with the headers looking like this, the destination being 0100, source IP address being 1101. Okay. Now we need to go ahead and look up the flow table in this router, and then determine it should go out on interface 2 arriving at this router next. Now in order to do that, there needs to be an entry, let's say this one here, matching the destination and source address. So in the header column of this entry, there should be specification looking like this. D equals 0100, S equal 1101. Therefore, when this packet arrives, look up, we match this entry, and therefore take the action here. Now, forwarding to interface 2, the action there should look like this. Okay, so matching this packet to the combination of header fields and take the action. Now, in the meantime, we take the action, this thing here. Okay, for this entry, the counters, both the packet counter and the data byte counter will be added. So packet counter will be added by 1 for one packet. Data counter will be added by the size of the data here in the packet. Okay, so you see, header column here for matching purpose. Last column here for action purpose. And counter here for management purpose. To put in simpler words, we take a combination of these header fields with specific values and we define that as a pattern, okay, for a flow. So whenever there is a packet coming in, the SDN router is essentially determining which flow the packet belongs to, because that flow entry is going to tell the SDN router how to handle the packet. That is called the generalized forwarding. So step number 1, the most important step. For each incoming packet, take the header. Try to match the various patterns, okay, in the flow table. If there's a matching entry, go to the action column, so that's step 2, and then handle the packet that way. It could be simply to forward the packet to the next router, or drop in the packet, or modify the packet, or send the packet to the remote controller. So that is usually for debugging purpose, by the way. And step 3, increment the counter so that we track number of packets matching to the flow, number of bytes, okay, matching to the flow. Now, priority. Yeah, so this is something that we have not yet talked about, the priority column. Okay, so the flow table should have actually 4 columns instead of 3. Let me explain why we need priority there. Yeah, these patterns, okay, in the flow table, some of these patterns could be more coarse-grained. Many of the packets might match the pattern. Some might be finer-grained. Okay, few packets will match the pattern. So if we have multiple patterns that are coarse-grained, chances is actually high that they overlap. Okay, therefore, for a packet incoming, that packet could potentially match to multiple patterns, multiple entries, and each entry specifies an action. So, which actions do we take then, right? So priority there, okay, is to specify which pattern carries a higher priority and which one carries less. So we could differentiate or break the tie among all the matching patterns. Which one should be taken priority, therefore we take the action, okay, in the prioritized entry. Okay, so priority there is to disambiguate all the matching entries. Now in traditional forwarding, we don't need to specify a priority. Why? Traditional forwarding there is to do what? Prefix matching. We do have multiple prefixes existing in the forwarding table. So one packet could actually match to multiple prefixes. But you know what? In traditional forwarding, we are also doing the longest prefix matching. That actually breaks the tie naturally, because there's only going to be one longest prefix. Okay? Unlike in SDN, we could have multiple patterns, and the patterns are now general, right? It's not always prefix, so you cannot use the lengths to break the tie. So we have a specific priority field there to break the tie. Okay, so the forward table in a router, 4 column, and it defines how the SDN handles a packet. It defines the match and action rules. To be more concrete, let's look into 3 examples. Now, in all 3 examples, we look at the source address and the destination address header fields. Now, in example number 1, we don't want to match the source address being 1.2.1 something. Okay, so the asterisk here meant wildcard, meaning arbitrary values for the last 2 octets. Destination address must match 3.4.5 for the first 3 octets, and then doesn't matter, okay, what the 4th octet is. Now, all packets matching this pattern will be dropped. In second example, source can be anything, but destination address needs to match 3.4 something. And then we forward all those packets to interface 2. Third entry, 10.1.2.3, as long as the source IP address is exactly this, we send the packet back to the remote controller. So 3 examples. You get a rough feeling. Now, let me come back here. I have not yet explained what OpenFlow means. Yeah, this is the data plane abstraction for SDN routers, all right. Okay, what does OpenFlow mean? Okay. OpenFlow, capital O, capital F. It's a very specific term. It is the protocol, okay, defined for communication between the data plane router to the control plane remote controller. Okay, so remote controller installing forwarding table using the OpenFlow protocol.
And so that was the first part of SDN, and we'll play the second part of SDN next week. And now we move on to PA9. PA9, this is also the last Golang assignment. What you'll be asked to do is very light. Simply extend your web file server such that it's secure. Now, by secure web file server, I meant that your web file server there exchanging HTTP messages with the client. All these messages will be encrypted so that any hackers, okay, in the middle of the internet somewhere, after sniffing the traffic, examining the content of the packet, will not be able to see what you want to say with the remote process, with the client process in plain text. And that is not very hard to do. You will need to learn a couple more APIs, but very straightforward. So after calling these new APIs, what you'll be creating are the secure sockets instead of the regular sockets. As a result, the messages you'll be sending out would all be encrypted. And that secure socket is called the TLS socket. Now, TLS we've already introduced in chapter 2 when we were talking about the QoS, quality of services. So one of the 4 quality of services that we might need to provide for application need is security. Okay, and that is when I talked about TLS. So it's the support there in the application layer, but right above TCP, the transport layer, and right below the application process. So it's application process, TLS, TCP. Okay, so it belongs to the application layer, but it's at the bottom of the application layer. Okay, as a result, at the application process, you generate message, you push it through the TLS socket. The TLS socket encrypt the message before it passes further down to TCP, pass further down to IP. Okay. So the hackers in the middle, even though they intercept the messages, it's going to be encrypted anyway. They will not be able to see, okay, what is the secret you want to transmit to the remote process. The thing is that this encryption is done using a shared key between the sender and the receiver. So the client sending requests will need to encrypt the HTTP request messages. The web server there sending the response will need to know the shared key to encrypt the HTTP response messages. Okay. The problem is, right? Yeah, the client can generate the shared master key, but how does the shared master key get to the hands of the server, right? Otherwise, the server does not know how to decrypt the encrypted HTTP request. Server doesn't know how to encrypt the HTTP response messages that needs to be secret. So, yeah, there's an issue distributing the shared master key. And that is what's magic in TLS. So, yeah, the connection using a TLS socket is actually separated to the key establishment phase to the data phase. So in the key establishment phase, this master key, okay, is distributed without anyone else knowing. Now, when the server and the client both have the shared master key, then in the data phase, they use the same shared key to encrypt all the messages. So the magic is right there in the key establishment phase. The way it works, however, is not that hard. It's only a three-way handshake, just like establishing the TCP connection. The client here, being the one initiating the connection, sends a hello. That's plain text. And there's nothing secret about the hello message. Okay, it's just that, hey guys, are you there? Okay, server there, being present, sends back a message, and that message doesn't need to be a secret. In that message, it contains the server's public key. Okay. So by public key, what it meant is that this key can be well known by everyone in the world. Okay. So client here will see, oh, server's public key, cool. And then here, this is the magic. The client here sends the master key, but the master key is encrypted using server's public key. All right. Now, when that message arrived at the server can decrypt the message using the server's private key. Now, server's private key is private. Only the server keeps it. Okay? No one else on the internet knows about the private key. That's why the master key being encrypted by the server's public key is kept a secret, and only the server will know what the master key is. And this is done by the magic of this public key system, where if you have a message that you encrypt it with the public key, only the private key can decrypt it. If you have a message encrypted using the private key, only the public key can decrypt it. And so the server there needs to have a pair of these keys, the public key so that it can send to the client, the private key such that the master key coming from the client can be decrypted. And that is what I meant here. You need to set up the public and the private key file, okay, when we call the TLS socket establishment API. And no worries, Poly has already created the key pair for you. So server.ser here is the public key. Server.key here is the private key. Okay. So you just download these two files and put them into the PA9 directory where you'll be working in for the examples to come and for the PA9.go, okay, that you will submit. Let's go ahead and start with the first example. It's called the secure HTTP using the TLS listen. Okay. Listen L there being capital. So this is to contrast the regular listening socket. The way we create the listening socket is by calling net.listen. Again, listen there, L being capital. And this is for those who took the native string approach for PA7 and PA8, where you read one string at a time or write the HTTP responses one string at a time. Okay, so let's start a file. Okay, and let's name it sec string response.go. Yeah, you probably guessed this is the secure string response.go example. And so don't be surprised, it looks very much like the string response.go in PA8. The only line being different in the header part, so package main, importing bunch of packages, and then the check function, okay, to do the panic check. The only line being new is just this. Okay, so we're importing a new package called the crypto/TLS. Yeah, no surprise here either, because we're calling the TLS sockets. Therefore, these APIs to create the TLS socket, control TLS socket, is defined in the TLS package. Now, in the main function, there's slightly more differences. So these two lines, completely new. All right, so these two lines are there to configure the public key file, the private key file, to the TLS socket. All right. We'll go through the code in a little bit, Okay, so we'll take the code walkthrough a little bit later. Let's quickly go through the example, right? Now, these look familiar again, right? So, format print line launching server, okay? Creating the listening socket, close the listening socket by deferring to the end of the process. Okay, getting a call from the client. ln.accept, accepting the call. Okay, and deferring closing of the socket, the data socket, at the end of the process. So the TLS.listen, okay, is the one being different. Previously, this API was simply net.listen. And by calling TLS.listen, be very careful because we need to tell the public key and the private key to the TLS socket. So that is done here. By adding one more parameter, it's the config, okay, objects pointer. And the config object is already assigned here by calling, okay, tls.config. And the cert here, the certificate or the public key, is actually established calling the load x509 key pair. So this is to load the key pair, the public and the private key, to the certificate. And then the certificate here is defined into the config, the object. And the config object here is later, okay, being used to specify, okay, the listening socket. And that listening socket is now secure. As a result, all the subsequent socket created is going to use the share key there being exchanged here to ensure transmission of secrets. Now, all these lines, okay, subsequently in the main function remain the same. Running of the example is very similar to the examples in PA8. The only two minor differences are these. After we start the server process, the seq string response.go. Yeah, we use curl again, the command line web browser, to try to fetch an arbitrary web object. But this time we use the -k there in addition. So the entire line we will actually type up from the client side is curl -k. Okay? And to add to that, we are now doing what? Secure HTTP. So make sure that you specify the protocol HTTPS column / and then the URL. If we did not specify HTTPS there, the protocol, by typing just 127.0.0.1 column port number, the default is the not secure HTTP. Okay, so make sure you type up the whole string here, okay, while doing the testing. And yeah, this example is going to just show, okay, what's in the data part of the response message, which is file not found. And then we return to the prompt. Let's demo now. And this is pollys PA9 directory. So you see pa9.go is already implemented, and the example secure string response.go is right here. Oh, you see also, by the way, the public key and the private key downloaded and put into the pa9 directory. Let's go ahead and give it a try. Run the secure string response.go. All right, server launched. And now we curl with the K flag and specifying this is secure HTTP to the server. And the port number, the server process is running there. The server there is always sending back message saying file not found. So curl here is showing the content of the response message. And server side here prints only the method of the HTTP request message, and that's what we're seeing here. Okay. Why don't we try curling without HTTPS and see how it's going to happen, how it's going to go. So just this. Oh, and we need to start the server running again. Right. And curl. Right. Curl is not getting any reply back. Let's see what the server side is complaining. All right, so there's a panic message and the TLS package is complaining. First record does not look like a TLS handshake. Yeah, so the client here handshaking to the server. But that handshake message is not HTTPS, okay, handshake, not the TLS handshake. Therefore, server side is rejecting, okay, to the request and not sending anything back. So curl gets nothing back. Okay, and the server side is simply jumping and panicking. Now you might be thinking, how do we know the messages being exchanged are really encrypted? Now let me use a traffic sniffing tool to demonstrate that a hacker could be sniffing the packets and trying to see the content of the packet. And let's run the example again and see if we get to see the content of the messages being exchanged between the example server and the curl client. So the tool I'm going to use to sniff the traffic is called TCP dump. Okay. So on Mac OS, okay, TCP dump is just right there. It's a very basic tool to check, to debug whether the network is going okay, what packets are being exchanged, and what packets might get dropped. So TCP dump, and I'm going to use the big A flag so that I can see the content of the packets. And I'm just going to sniff on a particular interface that the packet is going to travel. And because I'm sending to localhost in the demo, so I'm just going to limit the packets that I sniff to all that goes to host or coming from host 127.0.0.1. Let's go ahead. Oh, wait, you don't have permission to capture on this device. Okay, yeah, so I'm just going to use the root access. Sudo is allowing me to give the password of the root so that I can start the TCP dump. There, TCP dump now working. So it's waiting for packets to travel through the interface. Let's go ahead and run the example. Secure string response.go. All right, server running. Now HTTPS. Okay, so client side behaving as expected, server side behaving as expected. And we do see here TCP dump is actually, printing lots of information here. Let's go all the way back to the start of the TCP dump command. Yeah, quite a bit of messages being exchanged. Quite a bit of the packets being exchanged. There. Okay. TCP dump. Let's see the first packet. Yeah, right here. 5 p.m., 17 minutes, 28.0643667 seconds. And this is an IP packet coming from this host, local host, and this port number, 52158. So this must be the client here on the lower right. And it's going to localhost 127.0.0.1 and then port number 11999. Yeah, that's the port the example server is running. So this must be the first exchange message to establish the connection, right? The second one then must be coming back from the server and to the client. Then this must be the response containing the public key of the server. There. And if we go down further, you see that all these messages look like random codes. Random codes. Yeah, chances high. The messages being exchanged between the client and the server are indeed encrypted. So you see here, length 45. There should be some 45 real data being sent over this packet. All right, but that 40 byte encrypted right here. So we can see the plain text not being able to understand what's being exchanged. Now let's try, sending messages without encryption, without the TLS socket. How about that? Let's Go back to PAA and see if we get to see the packet content and see the real message being exchanged. And let's run how about the string response.go? Okay, running. And now let's curl without the S and without the -K flag. There. Okay, client behaving as expected. Server behaving as expected. Again, in TCP dump, we see lots of output. So TCP dump is printing packet by packet, okay, all the content, okay, with the big A flag. Let's go all the way. Yeah, I think this is where I started the second example without encryption, the non-TLS socket example. This is the first packet, again, coming from the client port to the server port. And yeah, the message looks encrypted. I can't tell what's going on. Second one, coming back from the server to the client, I can't tell either. If we scroll down, oh wait. Yeah, so the first message here, second, third, fourth, fifth. Look at the fifth message. Okay, coming from the client to the server. What do you see here? Yeah, it starts by, a bunch of these random codes, but get /http/1.1. What is this? We actually know, right? Because it actually fits HTTP request message format. This is the HTTP request message coming from the client to the server. Let's see if we get to see the reply from the server. Right here. The first line in the HTTP response in one packet. Second line, date, column, ... in the second packet. From the server back to the client. Again, the third packet from the server back to the client. But it's an empty line, so nothing here. Fourth, from the client to the server. Yeah, nothing. It's a length 0, so this could be a keep alive or something like that. And then from the server again to the client. Length 15. Oh, the data, file not found. And something coming back from the client to the server, and finally server to the client. This should be the /r/n. And then client sends something further back to the server. Yeah. A few more messages, but none of these comprehensible. I'm guessing that these are trying to close the connection. Okay, server here ends finally with yet another closing message. And so you see, without using the TLS socket, we get to see the content of these HTTP requests and response messages. Ouch. And before we start with the code walkthrough, in case you're interested in sniffing your own packets that you generate between the client and the example server, download Wireshark. Wire, the cable, W-I-R-E, shark, the fish shark. Google it up, download, install. Play with it a little bit. It's not that difficult. You should be able to see the content inside the packets you're sending. Okay. Now, code walkthrough. The key API is this one here. TLS.listen. So this is the key API allowing us to create the TLS socket, the secure socket. In contrast, a regular socket, we use the net.listen. Okay, the net.listen is defined in the net package. TLS listen defined in the TLS package. What might look slightly complicated are the two lines to configure the TLS socket. But generally what you can do is just to copy the two lines in the example and then replace it in case you generate different key pairs. The key pairs just need to be specified in this API, load X509 key pairs. So I think the first parameter is the public key, second parameter is the private key. Now after that, we have configured the TLS socket, all right? And you heard earlier, okay, in order for the TLS socket to work, there's the key establishment phase and then the data exchange phase. In the key establishment phase, the client sends a hello to the server. Server sends the public key back, which is also the certificate. So cert here is the certificate generated from the public key. Okay, so sometimes I kind of just call it either certificate or the public key, but when I use either term, I actually meant the same thing, all right? Okay, so when the client tries to connect to the server, okay, the certificate will be sent to the client, right? And then the client will be using the public key to encrypt what? The master key. But what I did not mention there explaining TLS is this. Before the client encrypt the master key with the public key of the server, the client checks, okay, whether the certificate is really valid, okay? So it's gonna check to verify the certificate through a third party, a certificate authority, the CA. Usually a government will actually establish a CA, okay? Those web servers that are trying to provide secure service would register their certificate to these CAs. Okay? And therefore the client can check whether the certificate is really valid by sending the certificate to the CA. Inside the certificate, it's containing the organization's name, the server's name and stuff. So the CA is going to validate, okay, this is indeed the server and this is indeed the certificate. Okay. When the client gets a reply from the CA saying that the certificate check is passed, then the client encrypts the master key using the certificate back to the server, and then the secure data exchange phase begins. But you see, the public key or the certificate needs to be registered to the government CA. All right. Now, this CA, in order to be maintained and running in a self-sustainable way, usually the server needs to pay the CA a certain amount of money. All right. Unfortunately, for the PA's purpose, okay, Poly is not paying the CA to register an example certificate. Okay, so server cert here is not registered to any CA. Therefore, the curl client there, okay, if it's checking whether the certificate is valid, it's gonna fail. So for the curl to pass, -K, this flag's purpose is to suppress the CA checking process for the certificate. Okay, so it's to bypass that in the key establishment process connection. So you can also try to use a Firefox browser, okay, to request https:// localhost and your port number, and see how the browser, okay, shows. Chances high, the Firefox browser is going to complain, okay, that certificate is very, very risky. CA cannot validate it. Okay, are you sure that you want to proceed? Okay. If you click yes, proceed, Firefox is going to record the certificate in the exception list. Okay, so that later on, if you go to the same server, Firefox is going to make the exception and allow you to access the website. Okay. So if you reload, okay, the second time, you'll see Firefox shows file not found. Let me demonstrate using Firefox to access a web object using TLS socket. So Firefox, all right. And start the 6-string response.go server. All right, it's working now. And HTTPS, localhost, port number, that. Okay, let's see. Oh, there. You see server jumped. Okay, so panic. Remote error. TLS socket is complaining. Unknown certificate authority. Ooh. And Firefox, the web browser, is complaining, your connection is not secure. Ooh. So this website is configuring the website improperly. So yeah, Firefox is advising you not to connect to this website. Okay, so go back is actually highlighted in blue, okay, looking more obvious. So go back. But one can actually choose the other box called the advanced. And by clicking advanced, you see 127.0.0.1 column 11999 uses an invalid security certificate. Okay, so the certificate is not trusted because it's self-signed and it's not registered to the certificate authority. Yeah, because Poly did not register it because I need to pay money for this. Okay, so one could actually do this. Add exception. So click the add exception box. So that's going to add the certificate that Poly has provided, okay, as an exception. So next time we'll be able to access 127.0.0.1 column 11999. So let's view the certificate, how it looks like. All right, so NTUEE and the organization type is EDU. Yeah, so this is indeed what Poly has created. So let's confirm the security exception. Now we can try it again. But let's see. Yeah, the server is off. Let me start the server again. Right. Try again. Here. There. So we finally get the string coming from the server, and the server is actually exiting as it is supposed to. The second example is secure HTTP using listen and serve TLS. So this API here is part of Golan's building web server. And this API will be very useful for those who do PA7 and PA8, borrowing from Golan's existing code for the building web server. Okay. Now, let's see if this example will inspire you in terms of changing your PA8 so that it will work in a secure way. So this example is called the sec handler response.go. Yeah, so it's a slight extension of the handler response.go in PA8. So if you look into the code, you'll see that, well, in fact, all the lines are the same except for the very last line here. http.listenandserve TOS. Okay. Originally in PAA, it's only http.listenandserve. So that is the API to start the server listening and begin serving files. Now, adding the TLS here is essentially indicating the API is extending listen and serve to do secure listen and serve. Okay. So this server process here is going to be sitting on top of TLS and TLS on top of TCP. The slight difference between listen and serve TLS to the original listen and serve is here. So this API now takes in 4 parameters. Okay, in addition to the port number, the server will be listening. In addition to this nil here indicating that it's using the default serve mux, we need 2 more parameters, which are the public key and the private key file. Now to set up the TLS, the keys are required. Now, we may start testing the example. Similarly, we will start the server process first, and then we'll use the command line web browser curl, okay, to give it a try. So again, we'll be using curl-k, the K flag, so we can bypass the CA check because Poly does not want to pay the CA for just assignment purpose. Now, these are some of the comments you can try. So first of all, in PAA, if you recall, to test the handler response.go, okay, we try doing what? The hello. Yeah, this is a prefix to trigger the hello handler. Now for all the other prefixes, it should go into the file server, the default file server, the building file server. So sec string response.go should actually what? get the sexstring response.go file, the content in there. And QWERTY.htm, which is a file not existing, so that is a random file. This should give us a file not found, right? Oh, and by the way, yeah, in addition to the -k flag, make sure that you are asking HTTPS, this protocol, to respond. Before we do the demo, let me just go through the code. Let me just walk through the code because it's very straightforward. The only line being different is just here. Okay, listen and serve, TLS. And it is simply the equivalent of listen and serve, except that it's doing the TLS secure socket. Okay, usage is slightly different, which I just explained. Yeah, and now let's go to the demo. Now here's the demo. So we'll start the server process first. The handler response.go. All right. And we now curl -k in HTTPS to the local host. Yeah, let's try. How is hello handled this time? There. Okay. HTTPS working, and then it gets us the string hello world. Okay. So this is what the hello handler is supposed to do. Let's try to grab an existing file. I think the server test is still in my directory. There. Yeah, we get the content of the server test.html. Now let's grab a non-existing file. Let's say .txt and see. There. Ooh, page not found. Okay, so this is the response coming from the built-in web server, okay, in Golang. Great. What should we do now? Oh, yeah, we could do the TCP dump to see if indeed these HTTP messages being exchanged are encrypted. So let's do the same. TCP dump -n not to convert the IP addresses to the name, and -a gives us the entire content in the packet. -i is only monitoring the loopback interface, LO0. Okay, and I'm just gonna sniff packets that come from or go to 127.0.0.1, given that the example is right there on the local machine. Okay. Yeah, to run TCP, root access is required. Oops, wrong password. Sorry. There we go. Okay. So now let's try to the handle. Okay, how about that? Hello handle. Hello. There. All right, so there are quite a few packets. Okay, but focus on this part of the output and see if we get these HTTP messages. Okay, the plain text being printed. Very good. All encrypted. Can't tell what's inside, you see. Can't tell what's inside. Yeah, this is probably the part that the certificate is being exchanged. So you see NTUEE, EDU. Yeah, right there. Pao Yi Huang. Yeah, this is the one, the email signing the certificate. Yeah, self-signed by Pao. Yeah, you see a little bit of information, but it's actually higher level. We do not see the content of the HTTP request or reply message. Yeah, this is where I started the TCP dump. All right, so good. We did not see, okay, anything really seriously in plain text, okay, this time. All right. Yeah, I know. So maybe we go back to PA8 and see if we could see the content, right? Running the handler response.go. Okay, let's see. All right. Good, I'm still getting the hello.world, so server is working. And you know what? Right here, okay, we see the response coming back to the client. So yeah, this is the server, IP address, port number coming back to the client. Yeah, you see very clearly, yeah, the status line. There's one header line saying the date, another header line saying the content size, and the format, and then an empty line, and then the data, and then the ending line. Okay, so without listen and serve TOS, yeah, we see the messages in plain text, and I guess this is a request indeed. Get slash hello http slash 1.1. Right, so that's the demo. And that was pretty much PA9. And there's 3 minutes remaining, but what I'm just going to say is very simple. We'll play the video for the second half of SDN next Wednesday. And then right there, we'll start chapter 5, the routing part, the control plane, okay, of the network layer. So that part is way more interesting than chapter 4, the data plane. Okay, so try to tune in, and I'm going to leave the session on for just a few more minutes in case you have any questions. And otherwise, if you don't have any questions, just feel free to go and have lunch. Okay, so I guess that's all. I'm going to end the stream right here and see you next week.